So hello and welcome to our seminar. This time Alicia is going to talk about some individual study, namely about the mathematics of artificial intelligence, new book. And today she's going to report on chapter 5. So that being said, I now pass the focus spotlight in Zoom, and you're free to share your screen.
Thank you. Can you see it now?
Yes.
Okay. Hello, everyone. Again, I'm Alicia, and today I will tell you about Chapter 5, explaining the decisions of convolutional neural networks. This is the contents of today's presentation. I will start with a discussion of why the need for explainability of deep neural networks has arisen in the first place. Then we will consider how it can be measured in the example of linear models. And from that point on, we will consider nonlinear models that are a bit more difficult to explain. I will list some methods for nonlinear models and elaborate on one model's theoretical foundation. Well, let us begin. Over the years, machine learning models have grown in complexity. This is how typical linear neural network used to look like, and how it grew more and more complicated with the usage of additional hidden layers. When we feed a neural network some input, for instance, an image, we receive just the output layer information, for instance, a description of what is depicted on the image. It seems impossible to infer or reasonably guess how the model reached its decision, namely what was going on in the hidden layers. Nowadays, when we can build more and more intricate models, their accuracy is often achieved at the expense of interpretability. After being fed with large amount of data, deep learning models can achieve record performances, but it remains quite difficult to explain why they reach their decisions. However, some methods have been developed recently that can explain models' decisions post hoc. Let us discuss them. First of all, let me note the advantages of explainability development. It allows inspection and debugging of the models, which in turn can help to discover so-called clever Hans predictors. Those predictors rely on spurious artifacts in the data and, in fact, do not solve the problem. They are named after a horse, Clever Hans, that supposedly solved simple arithmetic tasks, but in fact inferred the correct answer from the body language of its instructor. An example of Clever Hans in machine learning would be a model that is supposed to interpret the image, but it relies not on the image itself, but on its file name, for example. There are some other advantages of explainability, except the opportunity to root out the incorrectly working models. The model's explainability is also required in autonomous driving or medicine or other fields that deal with humans' health and life, and therefore it is impossible to use models that can be possibly wrong in them. The explainability is also required to avoid discrimination, for instance, in models that consider eligibility for bank loans or models that review job applicants. For instance, the European Union's General Data Protection Regulation explicitly mentions the right to explanation for users subjected to such models. Lastly, the analysis of neural networks can provide insights into the unknown relationships between the studied features and thus help discover some scientific laws. Now that we understand how important can explainability be, let's discuss what it is. So an explanation or heat map is considered to be a collection of relevance values having the same dimensionality as the input. For example, for this image of the cyclist, that's how heat maps of models that interpreted it as a bike or as a person would look like respectively. As we can see, the explanation has to have some faithfulness, meaning that each relevance value, which is a real number, should show how much the corresponding input has contributed to the overall classification decision. For instance, on these heat maps, the red colors denote a higher relevance value, green denote low relevance value. To check whether those criteria were met, three quantifiable aspects of explanation are used: conservation, model data interaction, and signed relevance. Conservation suggests that the summed relevance values should be approximately equal to the total evidence at the output of the network. Model data interaction states that an input feature on its own cannot be regarded as relevant or irrelevant. So there should exist a possibility of it being used for explanation as a part of one input, but not necessarily the others. And finally, signed relevance requires the meaningfulness of the sign. More precisely, it means that positive relevance values should correspond to features relevant to the decision, and negative values should correspond to features contradicting the decision. However, even with all these requirements, the task of explaining linear model is still rather simple. But first, let me remind you what a linear model is. It takes vector as its input and returns a linear combination of the input values as its output. But accordingly, a model is called nonlinear if the output function it returns is nonlinear. Thus, for linear model, the relevance values can be defined as follows. A similar result can be achieved for overall nonlinear but locally linear model through well-known Taylor expansion. If the function is twice continuously differentiable at the reference point x tilde, then it can be decomposed as follows, taking the relevance values as these terms. If we choose a root point, if we choose a reference point as a root point, and because of its linearity, we can see that conservation property holds. F theta of x is approximately equal to the sum of relevance values. Unfortunately, the task of explanation becomes a bit more difficult for the rest of nonlinear models. Throughout machine learning development, there were introduced several types of methods for their explanation. Those types are surrogate-based method, perturbation-based method, and propagation-based method. The surrogate-based method utilizes the fact that simple linear classifiers are easily explainable because they can be decomposed. This method approximates models locally with simple interpretable surrogate function, hence its name. Thus, they do not need to access the internal structure. Nonetheless, they need a sample of input-output pairs, which is often computationally expensive. The next type, perturbation-based method, constructs explanation from model's response to local changes, for example, some perturbations. This approach can be expressed as optimization problem trying to identify a minimal set of relevance input features. The last propagation-based method explains the decisions of neural networks utilizing the internal structure of the model. It runs a purpose-designed backward pass in the network, and therefore, unlike surrogate-based method, it does not require sampling. It seems promising, so most of the recent work in the area considers this type of method. One of the most common types of propagation-based method is Layerwise relevance propagation, which is the main topic of today's talk. Layerwise relevance propagation, which is also called LRP, implements a reverse propagation procedure from the output to the input as a collection of redistribution rules applied at each layer of the network. It can view the backward pass as performing a number of Taylor expansions at each level of the network. Naturally, just like before with Taylor expansion, the conservation property holds, and it can be described mathematically in this way, where the square brackets denote the number of the layer, and n with respective subscript refers to the dimension of its input. The figure on this slide illustrates an example of a reverse propagation procedure implemented for a convolutional neural network. As we can see, it takes separate pixels, processes them, and at fully connected layers arrives to its prediction that the image depicts a rooster. At every layer, the activations are computed with this formula. I think the quality is better here. Where sigma is the activation function, and in this example, it's equal to the maximum of its input and 0. It includes all the lower layer activations and an extra bias term. The LRP method redistributes the relevance values proportionately to the contribution of neurons in the forward pass. And we can see that the different formulas for redistribution rules are used for fully connected layers and for convolutional layers. And I will later explain what techniques are used for different layers and why. For that, let us discuss the theoretical interpretation of the LRP method. Namely deep Taylor decomposition, often referred to as DTD. DTD uses Taylor expansions not to attribute directly the network output to its input, but at each layer to attribute the relevance scores to the neurons in the layer just below. So it provides relevance transition between the neurons of the two consecutive layers using the approximation of the relevance locally. Here is the formula for the approximation that takes place in the case of that rooster picture we just considered. It holds for the last layer, and it also can be shown that if it holds for a layer, it will hold for a consecutive lower layer. So we can infer that we can safely use the DTD for all the layers in this model. For the activated domain, there is no relevance to consider for DTD. For an activated one, the consideration at the reference point gives this approximation where higher order terms cancel because we can use the fact that the activation function is linear at the activated domain, and the first order terms can be reduced to this. Thus we can receive how the value is how much relevance from neuron K at layer I should be distributed to the neurons on the lower level. After finishing the redistribution of the relevance from each neuron on the higher level I to the lower level neurons, we can calculate the lower level relevance values. And for that, we just sum all the relevance values that transferred from all the neurons at higher level to this particular neuron on the lower layer. Now let us consider what LRP rules for relevance function can be used at different layers to implement DTD efficiently. This table summarizes some of the rules which are most often used for the redistribution rule we just saw. As we know, the result of applying those rules is a heat map highlighting the pixels which have contributed the most to the classification of a particular image. The LRP0 rule, the simplest one, has a root point at its origin, which might be far from data and result in noisy explanation for deep networks. It should be used only for simple functions, for instance, the very top, usually fully connected layers of a neural network. The LRP epsilon rule adds a constant to the denominator and thus stabilizes as a distribution process. And it is the case that the relevance of neurons with really weak contributions is driven to zero by this approach. And it is also observed in practices. This rule is also quite useful, mostly for fully connected top layers. The LRP gamma and LRP alpha beta rules, however, can be used for lower convolutional layers. However, they assume only positive input. So they cannot be used for the first layer because the input, for instance, pixel scores can be potentially negative. These rules help to distinguish between the supporting and contradicting explanatory factors. Now, let me sum up the key points of today's talk. We discussed the importance of explainability and its numerous advantages, among which there were a possibility to find the incorrectly working models, the people's right to explanation of the models, and lastly, opportunities for advance of science, so to speak. Layerwise relevance propagation method for nonlinear models. It can be used to achieve this explainability, and it considers its foundation is Taylor-based decomposition that uses different relevance approximations for each level, thus resulting in quite accurate explanations. That's all I wanted to tell you today. Thank you very much for your attention. Please ask questions if you have any.
Yes, thank you so much. Would you mind showing us the book where this chapter came from?
I will open a particular chapter saved separately. That's the chapter I was talking about today. And the book itself is called Mathematical Aspects of Deep Learning.
Right. Do you have the table of contents of the book also to share?
Just one moment, yes.
Right, yes. Yeah, so this is a very new book, and it's a large book on the popular topic of artificial intelligence with mathematical foundation, which AI indeed has been lacking. And you've chosen chapter 5 for your individual study. And maybe next time you will present another chapter, but we'll see about that. Okay, so now it's time for some discussion and questions. Well, Alexander, do you have a question?
Much about this.
Yeah, Alexander, remember we visited Seoul there with this guy, Roberto Zicari?
I know, yes, yes.
Right. And
I understand that this is related to what he's interested in.
right,
Yeah.
right, exactly.
Yeah.
Yes, I wasn't aware of this kind of research, but this is really spot on. It's kind of related to what we started discussing about stability.
Okay, okay.
Right.
Yes. I mean, yes.
Okay. Right. So then let me ask a question. So Alicia, if you were to continue in chapter 5 on explainability, is there something you would particularly want to study further? Or is there something you didn't understand that you want to study further therefore? Or is there kind of what is your personal takeaway? So you've made this talk, tailored it to the audience, 3 key messages to take home for the audience, but how about yourself?
Well, it would be interesting for me to explore the other methods used for LRP distribution. Like I described 4 rules, and as I mentioned, like none of them can actually be useful for first layer, which is the most complicated one. And there is a number of other rules, and the set of rules is quite limited because the rules have to be like the D2D has to be applicable for the rules. So it's interesting, like how different can the rules be upon this limitation, and how much are different there, how much different they can be for models that deal with similar topic.
Wonderful, yes. That's already the next step. Okay, I'll say more about that in person. Okay, so that concludes today's presentation. And how are your plans? Do you want to make another presentation about other chapters?
It would be great.
Okay, good. Then let's thank Alicia once again.
Thank you for the attention.
Okay, and I'm going to stop the recording.